Hello everyone, and welcome back. Last time we finished up with kinematics, and today we're going to start a whole new area, dynamics. Kinematics, remember, covers the description of motion without trying to explain why something has the motion it does. Now we're going to start the area of dynamics, where we're actually going to try and understand what's causing something to have the motion that it does. This brings us to section number 4, Newton's laws. Newton's laws, typically what we describe as Newton's 3 laws of motion, are going to be laws that we're going to look at one at a time to understand how they explain why things have the motion they do. These laws were developed by Sir Isaac Newton, who lived from 1642 to 1723 and was an absolutely amazing individual. Probably his most famous work, called the Principia Naturalis, is basically just an incredible mass of information describing physical problems. He also looked at optics, wrote a book about optics, incredibly productive. If you are interested, I would suggest a wonderful biography, Never at Rest, a biography of Isaac Newton by Richard Westphal. I read it. I really enjoyed it. If you have any interest in finding out more about Isaac Newton, the individual, that's a great place. So, to understand Newton's laws, we have to understand a new concept, a new type of quantity, and that is a force. Qualitatively, we can think of a force as a push or a pull. So, anytime something pushes on something else, anytime something pulls on something else, they are exerting a force. So I can push on this pen, I could push on it to throw it, so while I'm actually pushing on it to throw it, I'm exerting a force on it. I could pull on something, I could take this book and I could pull up on it, I'm exerting a force. But be careful, a motion is not necessary. So I can push on this wall, I can apply a force on the wall, and even though the wall is not moving, I am still applying a force. I can pull on this cord here. If I don't pull too hard and don't pull the screen down, I can pull on this cord, and even though the cord is not moving, I am still applying a force. So a pull in this case, push in this case. Anytime you apply a push or a pull, that's a force. Okay, so let's take a look at Newton's laws one at a time. Newton's first law of motion. An object remains at rest or in a state of uniform motion unless acted upon by an external force. So what does this mean? An object remains at rest. So that means an object that is stationary remains stationary. So a stationary object is not going to start moving unless a force acts on it. That makes sense. If you put something on a table, you expect it to stay there unless something comes along and knocks it off or pushes on it or does something to it. So if no force acts on an object, no external force. What does that mean, external force? We'll understand that a little bit more later. But for the time being, let's just think, as long as no force pushes on something, no net force. This is getting even more complicated. So what do we mean here? Just imagine there's something sitting on a table. So here's a table and there's a box sitting on it. That object will stay sitting on the table, not moving, unless some force acts on it. So that means unless something comes along and applies a force on it, it's not going to move. But what if we had an equal but opposite force pushing on it? So imagine I come along and I push with equal forces, equal pushes on the object in opposite directions. We expect it not to move. We still expect it to remain stationary. Well, this tells us something very important about forces. They are vectors. So we might have a force over here, F1, one over here, F2, for example. Forces are vectors. Not only is the amount of the force important, the magnitude of the force, but the direction of the force. And you can push things in different directions. Consequently, force is a vector. So as long as forces don't cancel out, if there is some net residual force, if you take all of the forces and add them all up as vectors, if there is some net force acting on the object, or let me go back, if there is no net force acting on the object, so there is no net force acting on it, then the object will maintain being at rest. It will stay where it is. It's not going to start moving without some net total force acting on it. So, remains at rest, or in a state of uniform motion. So what does that mean, uniform motion? That means moving at the same speed in the same direction. Well, same speed in the same direction, that means the same velocity. So it means in a state of uniform velocity, unless acted upon by some net external force. So an object, if it's moving, will keep moving at a uniform velocity if there is no net force acting on it. Now, while this being at rest, that seems to make sense, but the idea that something will keep moving, that's a little counterintuitive. That doesn't seem to agree with ordinary everyday experience, perhaps. Let's take a look at that. Let's look at something going on the lab bench. Here I have a little cart, and like we were saying before, if I were to just put this cart on the table, we expect it to just stay where it is. We don't expect it to start moving unless some force were to come along and push on it. Now, I can make it move by applying a force. I can make it move by pushing on it. But what happens as soon as I stop pushing on it, it stops moving. It doesn't keep moving. So where does the idea of it maintaining a uniform motion come from? Well, if we think about this, why is it stopping? It's stopping because there is a force acting on it. What is the force that's acting on it? There's friction between the cart and the bench. And it's that frictional force that's causing the cart to slow down and stop. What if we could remove that frictional force? Well, what if I use these very, very easily spinning wheels, and I put the cart here, and I give it a little push now? Well, now it just keeps moving, and it will just keep on moving unless some other force acts on it, like it goes off the end of the table and gravity pulls it down. So that seems to make a little bit more sense. If we could remove all of these external forces which we seem to live with all of the time, like friction, we could remove friction, then what's going to happen? Well, things do seem to keep moving much more than they do ordinarily, because friction is a force that seems to act on many, many things, if not everything, in our ordinary everyday life. And so it's this action of friction that actually causes things to stop. Okay, let's go back to Newton's law. Okay, so this seems to make more sense now. It makes sense that things that are stationary remain stationary unless something pushes on it. But now we have a better idea of why things maintain their motion unless a force acts on it. Things tend to stop, or things stop, because forces are acting on them, like friction or something like that. Sometimes we don't see the forces that are acting on things that are causing the object to stop, but that's actually what's happening. This helps us understand why it's so important for things like seat belts in cars and airbags and things like that. Imagine you're in a car and you and the car are moving down the road at 30 miles an hour. You know, maybe you're not on the highway or something, so on a road, and maybe you accidentally hit the car in front of you and your car stops. Your car hits the car in front of you and your car stops. Well, what's going to happen to you? You are also moving at 30 miles an hour, and you will continue to move at 30 miles an hour unless a force acts on you. Well, what force is going to stop your motion? Well, hopefully it'll be your seatbelt and maybe the airbag if it's a bad enough collision. If you don't have a seatbelt on or an airbag or something like that, you will just keep moving until you hit the front of your car, the windshield or your steering wheel or something like that. So you want something that's going to stop you safely as opposed to something that will stop you painfully. And because you're going to be stopped one way or another, there's got to be a force that's going to stop you and you just want that force to be as safe as possible. So that kind of makes sense why seat belts and airbags and things like that are important, because of Newton's first law. Okay, let's take a look at Newton's second law. Newton's second law of motion. This could be stated very easily mathematically, and it is F equals ma, where, let's remember, F, forces, are vectors, and so this is a vector equation. The vector force equals mass times the vector A, and well, what is that? Well, let's figure out what all of these terms mean. To apply this equation, this force is not just any force. If we are looking at some object, so imagine that we are applying Newton's second law onto some object. This force means the net force or the total force. So this means the net force or the total force acting on our object. So imagine that our object has got a number of different forces acting on it. Maybe there's a force like this, we'll call this one F1. And there's a force acting this way, we'll call that F2. And maybe a force this way called F3. And a force F4. And there could be F5, F6, F7, whatever. As many forces as we want. The force that goes into Newton's second law is the vector sum of all of these. So F, we might call this F sub n to remind ourselves this is the net force. Not just any old force, it's the total force. The net force is then the sum of F1 plus F2 plus F3 plus F4 plus whatever forces we have. It's the vector sum of all of the forces. And it's very important that we remember that this is a vector sum, not just the sum of the magnitudes. So if one force pushes this way and another force pushes with an equal magnitude but opposite direction, those two vectors would actually cancel each other out to give you zero net force. So the forces have to be added as vectors. So what's F? F is the net vector force acting on our object. A, what's A? A is the acceleration. That is the kinematic quantity that we have already looked at. It's just the acceleration of our object. So A is the acceleration. And M, what is M? M is the mass. We mentioned mass before when we were talking about our units, and the standard SI unit for mass is the kilogram. Qualitatively, mass is basically a measure of how much stuff something has. Let's leave it at that. Just leave it at a qualitative definition for now, but we'll come back to it. What I want to do is think about this equation, because there are different ways that we can look at or use this equation. F equals ma. Force equals mass times acceleration. Keeping in mind that the force that we're talking about is the total or the net force acting on an object. We can think of this in terms of the magnitudes of these quantities. So what does that mean? The magnitude of this side must equal the magnitude of this side. In other words, this is a vector and this side is a vector. Those two vectors are equal to each other. And if they're equal, they must have equal magnitudes. So that means that the magnitude of the net force must equal the mass times the magnitude of the acceleration. So this tells us something about the size of these quantities. Also, if these two vectors are equal, they must not only have the same magnitude, they must be in the same direction. M is just a scalar, and it is a positive scalar, so it can never change the direction of the acceleration. So this tells us that F and A are always in the same direction. So whatever direction the net force is, that's going to be the direction of the acceleration. Simply speaking, that makes sense. If I have an object like the cart and I push on it this way, it's going to accelerate that way. If I push on it this way, it's going to accelerate that way. So that kind of makes sense. But it can be a little bit more complicated than that. It can be a lot more complicated than that, as we'll see later on. So we'll talk some more about this later. There's another way of looking at this equation, and that is in terms of its components. So this is a vector, and this is a vector, and if they're equal, not only the magnitude and directions have to be the same, another way of looking at it is the components have to be the same. In other words, the net force in the x direction must equal the mass times the acceleration in the x direction. In other words, the x component of the net force must be equal to the mass times the x component of the acceleration. Likewise, the y component, Fy, must equal m-a-y, Fz must equal m-a-z. Okay, great. We will very often break this down and use it. We'll do this both ways. Sometimes we'll look at the magnitude. Sometimes we'll break it down and look at the components. All right, very, very good. Let's take a look at this a little bit more.